Theories of acid and base. We have different theories of acid and base. We have the first one. We have Arrhenius theory. We have the second guy. Bronsted-Lowry theory. We have the third guy. So we have these three theories of acid and base. We have the Arrhenius theory, the Bronsted-Lowry theory, and the Lewis theory. So we're going to be taking them one after the other, right? So let's look at the first one, Arrhenius theory. Arrhenius theory. Let's do that. Arrhenius defined an acid. Arrhenius defined an acid as a substance that ionizes to give hydrogen ion when dissolved in water. When dissolved in water. In brackets, aqueous solution. Sometimes they might not use the word water, they can just use the word aqueous. Alright? Aqueous simply means anything that has what? Water. Whereas he defined a base as a substance that produces hydroxide ion when dissolved in water. Please, this is hydrogen ion concentration. And this is hydroxide ion. So anytime I say hydrogen ion, this is what I'm referring to. Anytime I say hydroxide ion, this is what I'm referring to. Alright, so in exams, what are the possible way questions to be asked? They could ask us to define, or they will make a statement, and they put which theory of acid and base is this. Now, what is the disadvantage or the limitation of Arrhenius theory? It's very simple. Water needs to be present for anything to act as either an acid or as a base. That's already a limitation because there is a but. Alright, so let's look at examples of Arrhenius acid. Examples of Arrhenius acid. Examples of Arrhenius acid. We have the first one. Anything that we have all acids that can give H plus on ionization. The likes of HCl. Any acid you can think of that can ionize to give hydrogen ion is also considered Arrhenius acid. We have H2SO4. We have our CH3COOH. The list is endless. We have what are. Now these are examples of, there's nothing spectacular about Arrhenius acid, but there is something spectacular about the base. So let's look at example of Arrhenius base. Alright, we just saw Arrhenius acid. We have Arrhenius base. What is actually Arrhenius base, class? I gave us a point that said for Arrhenius base, all base that contains OH is considered Arrhenius base. Any base that contains OH can be considered Arrhenius base. We have the first one, we have NaOH. If this guy ionizes, OH has to be released. We have Ca this. We have KOH. We have we have OH itself. Any compound that, when you ionize that compound, it gives rise to OH, can be considered Arrhenius base. So in exams, they will actually give you 2 or 3 examples. They say, which of the following is or is Arrhenius base? And then they'll give you maybe 3 of these or 2 of these, and then they smuggle in other bases. For example, when we get to Bronsted, you're going to see that bases that are at Bronsted base, most of them cannot act as Arrhenius base. For example, Cn minus. This is a base because according to Bronsted, anything that can accept proton, right, is a base. This guy can accept proton. But according to Arrhenius, a base is something that can give out OH. This guy cannot give out OH. But this guy is a base, right? So this guy falls under Bronsted base. So in example, you can actually give us two of this and then smuggle in Cn, Cl minus. And they say which of the following things are not. So these are examples of Arrhenius base, and these are examples of Arrhenius acid. And with this now, we are done with Arrhenius theory. Please look out. This theory defines an acid as any substance that is capable of donating hydrogen ion, and a base as any substance capable of accepting proton. In other words, according to Bronsted-Lowry theory, an acid is a proton donor, whereas a base is a proton acceptor. Right? According to this guy, an acid is a what? A proton donor, while a base is a what? Proton acceptor. Alright. Example of Bronsted acid. All the acid I gave us under Arrhenius, right, can be considered as what? Bronsted. You know why? Let me show you why. According to Arrhenius says there must be water, right? If I add water here, it becomes H3O plus and what? Do you know that this guy can still dissociate without water? I can still have HCl giving us what? This guy is according to Bronsted, and this is according to what? So without water, this guy can still function as a what? As an acid. So take note of that. Example of Bronsted acids. All the acids I give us under Arrhenius acid can absolutely be classified under this area. We have HCl, even water, even HNO3, even H2SO4. The list is endless. Just when we talk about like Bronsted-Lowry base, we said it's not anything that has the tendency to accept proton. So I'm going to say, example of this guy is all conjugate base. I'll explain this. All conjugate base of acids are considered Arrhenius base. A conjugate base is always obtained from an acid as a result of the acid using a proton. Now that's point number one. Now there are still compounds that may not be regarded as conjugate base of an acid, but they are still considered as Bronsted base. We have water can be considered to be part of it. Even ammonia, etc. Now, why is water considered to be Arrhenius base? Bronsted base is because water can accept proton. If water accepts proton, water becomes H3O plus. If you notice, there is water here and there is water here, right? So compounds that can exhibit both acidic properties and also basic properties are known as what? Amphoteric. Now, there's what we call amphoteric, and there's also what we call amphiprotic. Alright? Now, what is the difference between amphoteric and amphiprotic? I'll explain. All amphiprotic are what? Amphoteric. Now, this guy is simply substance that can donate proton and can also what? Accept proton. This guy is basically based on proton. But we know that the concept of acid and base goes beyond proton, right? So there are compounds that are amphoteric, but they are not what? But water is amphiprotic by nature. Right? Maybe somebody asks you, why is not amphiprotic? But this one is just to boost your knowledge. Water is amphoteric, but if you want to break it down, right? Water is amphoteric because of the fact that it is what? Why? Water can give out proton and remain what? OH minus. Water can collect proton and become what? Right? So this guy is amphiprotic because he can give proton, can also do what? Accept proton. So by virtue of being amphiprotic, it can also be considered what? Amphoteric. Do you understand? So in case you're being asked an exam, substance that can act, that can function as an acid and a base is what? You have no business with this, right? Except they are the one that will mention this guy for you. But if they don't mention this guy for you, all amphipotic are also what? Amphoteric. See, if they ask you something that can act as an acid and also as a base is what? Because if this guy is this is a general name for this, right? So you have no business with this unless they are the one that will say this to you, right? Now, what is conjugate base? That's the big question now. Listen, conjugate base is actually a species, right? It's a species that is formed when an acid has lost just one proton. When an acid has lost what? Just one proton. For example, we have the conjugates base. We have this. HCl, conjugate base of HCl is what? Cl minus. We have H2O, conjugate base is what? We have HNO3, this guy is. We have H2, what's the conjugate base? SO4 what? SO4 2 minus. This is wrong. It's only conjugate base is what is formed when an acid has lost how many protons? One, just one. This guy can still act as an acid. If I have this guy as an acid, the conjugate base will not be what? But this guy can still donate hydrogen ion. So we have. Now this is an acid. The conjugate base for this guy will be. This base can be considered as Bronsted base. Why? Because they can accept proton. For something to form a conjugate base means that guy has lost proton. Is it not so? It means that if you give that guy back proton, it's going to do what? Accept. If you put proton back on this, it becomes this. Right? So all conjugate base of acids can be considered as Bronsted-Lowry base. Right? Which of the following is not what's the answer? According to this theory, an acid is any substance that can accept a pair of electrons to form a covalent bond. An acid is any substance that can accept a pair of electrons to form a covalent bond, whereas a base is any substance that can donate a pair of electrons to form a covalent bond. In other words, this is a new line. In other words, according to Lewis' theory, a base is electron pair donor. A base is electron pair donor, whereas an acid is electron pair acceptor. According to Lewis' theory, a base is electron pair donor, whereas an acid is electron pair acceptor. Now, so what's example of Lewis acid? We have this. We have this. Now, Lewis base is Arrhenius. Because this guy has a lone pair of electrons to donate. Amines. So this is the most, how will I put it down? The most common example of Lewis base. This guy can donate this item, this lone pair. So take note of that. For Lewis acid, we have H plus. This guy does not have any electron. It has an empty shell that can accept a pair of electrons. That's 2 electrons. Alright, now let's look at monoprotic and polyprotic acid and base. As the name implies, mono means one, poly means two. So what's the meaning of monoprotic acid and base? So we say monoprotic acid and base. First, please go down. These monoprotic acids are acids that can donate only one proton. Monoprotic acids, they are acids that can donate only one proton. Whereas monoprotic base is a base that can accept only one proton. Monoprotic acid is an acid that can donate just one proton, whereas the monoprotic base are bases that can accept just one proton. Now, example of monoprotic acid, HCl, this guy can donate only one, HNO3, only one, CH3, COOH. Now, example of monoprotic base. Can you give me an example of it? Let's add this guy. The list is endless. Can you give me an example of a conjugate base of this guy? Because this guy can only accept what? One proton. Etc. The list is endless. Please, polyprotic acids are acids that can donate more than two and more, please. Polyprotic acids are acids that can donate 2 or more protons. Polyprotic acids are acids that can donate 2 or more protons, whereas polyprotic bases are bases that can accept 2 or more protons. Please take note of that. Polyprotic acid can donate 2 or more protons, whereas polyprotic base can accept 2 or more protons. So let's say, example of polyprotic acid. We have H2SO4, H2CO3, H3PO4. This guy can donate 2 protons, 2 protons, 3 protons. And then a polyprotic base are the conjugate base of this guy first. We have SO4 2 minus, CO3 2 minus, PO4 3 minus. And we also have okay. Now this ethylene diamine is CH2, NH2, NH2. Now each amine has a lone pair. This guy can use this lone pair and accept 1 proton. This guy can also accept 1 proton here. Hydrazine is actually NH2, NH2. Please, hydrazine is this guy, put 2 here. Or you say N2H4, this is hydrazine. So it has 2 space where hydrogen can be bonded to. So why am I giving us this? Just in case, I also want to mention that an acid, after losing proton, will give rise to a conjugate base, whereas a base, after accepting a proton, will give rise to a conjugate acid. An acid, after losing proton, will give rise to a conjugate base, whereas a base, after accepting a proton, will give rise to a conjugate acid. An acid can only give rise to a conjugate base. A base can only give rise to what? Please, an acid cannot give rise to a conjugate acid. That will say, so therefore, an acid and its conjugate base forms That's the first one. The second one. Also, a base and the conjugate acid forms. So conjugate pair in exams, they might ask you to indicate the conjugate pairs. Conjugate pairs are always two. The one that comprise of the acid and its conjugate base, and the one that comprise of the base and its conjugate what? Acid. So most of the time, this stuff is always done in terms of a reaction, acid-base reaction. In acid-base reaction, the acid will give out a proton and a base will be there to accept it. So please. Now the common way this question can be asked is list out the conjugate pairs. First thing first, you need to know what conjugate pairs are before you can list it out. Is it not so? What are conjugate pairs? What are what? An acid and it's what? And a conjugate base. And a what? So first thing first, you need to identify which of these guys is an acid. Please, based on this reaction, an acid is not what you think is an acid that will be an acid. Are you listening? You don't actually use what you know already. You answer the question based on what is given to you on the board. Something might be a base normally, based on your understanding. But based on this reaction, you see it as a what? An acid. Now, remember I told us that this conjugate acid and base pair is as a result of Bronsted-Lowry theory of acid and base. You know? And that theory said an acid substance that gives out proton, right? Base does what? This guy initially had H. 1H, you know? On the product side, this guy is no longer having what? That means it has lost the hydrogen, you know? So this guy is the acid. And this guy that is formed after this guy must have lost the hydrogen is the what? Conjugate base. Right? So they say now once I've identified this one, I have gotten the other one. If there is an acid, here will be what? This base had 2 hydrogen before, is it not so? Yes. But here is not how many? 3. Now, how can you explain this? It's accepted. So this is conjugate. Now, we now say an acid so therefore the conjugate pairs, we have the first one, HCl slash Cl minus, and we have the second one, H2O slash what? Now these are the conjugate pairs. An acid, conjugate base. Base, conjugate acid. Claire, let me tell us something you need to know. Please take note of this, don't write. For every conjugate pair, right? Be it acid on base or base and acid, what is always going to differentiate both of them is just one hydrogen. How many hydrogen? 1. So if you see a pair that is differing from each other by more than 1 hydrogen, that is not a conjugate pair. Every conjugate pair has to differ with how many hydrogen? 1. 2 hydrogen here, 1. Look at it. Please take note of that. That's one of the ways you can, because auto-ionization of water can also be called self-ionization of water. This is a case where water reacts with itself as an acid and as a base. This is a case where water reacts with itself as an acid and as a base. Full stop. Self-ionization of water is a case where water reacts with itself as an acid and also as a base. Now we have this. Now this is water. One of them is acting as an acid, and the other guy is acting as a base. Equilibrium constant expression for water is called AW, or can also be called ion product constant of water. Now this is equals to the concentration of the product all over that of the reactant. But the reactant is actually in a liquid form. Liquid or solid doesn't take part in the equilibrium constant expression. So what we have here becomes this times what? It was supposed to be all over this, but I'm not going to because it's what? So I remove this. Now, at 25 degrees Celsius, kW is always 1.0 times 10, 14. So therefore, please note that this H3O plus is same thing as what? H plus. So this formula can be written, but this time around, instead of having H3O plus, we now have what? H plus. Now, when do we use this formula? Very simple. You can use this formula to solve for any one of these, when one of them is known and the other one is unknown. If you know the value of OH minus, you can use this guy to solve for H3O plus. And it is this formula that actually gave rise to pH plus POH equals what? 14. Calculate the molar concentration of H3O plus and OH minus ion in now this is a base. This is a base. Class, this base, is it going to give rise to H plus or OH minus? So between these two guys, which of them will I solve for first? Once I've gotten my OH minus, right? I can now use that formula I gave us here to get the what? So I'll come here, I'll say calcium hydroxide. This is a strong base, so it's going to dissociate completely. So this is going to be calcium 2 plus plus OH minus. This guy, as you can see, OH is how many here? So one mole of this entire compound will give rise to how many OH? So it's a must. So this is 1 is to 1 is to what? Now what was the concentration of this calcium hydroxide? 0.002. So if one mole of this gave rise to this, that means one mole of this gave rise to how many? 2. So this guy will be what? Which is 4. 0.004 is not so. So once you've done this, you now say so therefore my OH ion is 2 times 0.002, which is 0.004 molar. Now, but they asked us to solve for H3O at once. Now, you now say, recall that H3O plus times OH minus is equals to 1.0 times 10 to the power of what? Minus 14. Minus 14. It's not so. So therefore, if I make this guy, I know OH already, it's not so. If I make this guy subject to the formula, it simply means dividing both sides by H3O plus. So that, no? By OH minus. So that this guy can stand the load, it's not so. So if you make this guy subject to the formula, H3O plus. now becomes 1.0 times 10 all over what? Let's do this guy first. This is 1.0 times 10, 0.00. What's the answer here?
2.5 inspiration minus 2.
Molar. Please, is this stuff covering up this point? Is it showing this point? Alright, so this is the answer to this stuff. So this is actually how we can make use of that formula I gave to us, the auto-ionization of water. That formula. Please look up. Buffer solution. Buffer solution. A solution that can resist change in pH when a small amount of an acid or base is added to it. Let me explain this guy. In acidic buffer, the buffer action occurs at pH less than 7. Whereas in a base buffer, the buffer action occurs at pH greater than what? 7. And it's important for us to know that buffer is always a mixture of two things. An acid buffer is mixture of weak acid and a salt or conjugate base. Please take note of that. An acid buffer is actually made up of a weak acid and a salt or conjugate base. Now, example of an acid buffer is acetic acid buffer. Now, this is an acid. You combine this guy with the salt. Remember, salt is formed when the hydrogen ion of an acid is replaced with a metal. If you put this guy here, now this is actually a buffer solution. But most of the times, you can just have this with a conjugate base, which is CH3CO minus. So this is an example of an acid buffer, and this is the most common example of buffer solution you're going to be seeing. Alright? Now this is called acetic acid, and this guy is called sodium acetate. So in case you come across this, they say a buffer is made up of acetic acid and sodium acetate. So this is an example of an acid buffer, a weak acid and a salt, or a weak acid and its conjugate base. Alright. Please, right? Basic buffer is actually a buffer solution that its buffer action occurs at pH greater than 7. This guy is made up of a weak base and a salt or conjugate. You cannot use a strong acid to make a buffer solution. It's always weak acid and weak base and their respective salts. The most common example of this guy is ammonia. Ammonia is a weak base. The salt of ammonia is ammonium chloride. So in case you see this, now this is a buffer. This is base buffer. Or you can do conjugate acid of this guy is NH4+. Calculation of pH of a buffer solution can be done using the Henderson-Hasselbalch equation. Please, this square bracket stands for concentration. So take note of that. This square bracket stands for concentration, So this is pH equals to pKa plus, now how do we get our pKa? pKa is obtained by using this formula. They will always give you Ka. So for me to get my pKa, I'll simply press negative log of this to get the value of the pKa. Calculate the pH of a buffer solution composed of 0.12 molar acetic acid, composed of 0.12 molar acetic acid, and 0.20 molar sodium acetate. Now this is acetic acid. Now this is sodium acetate. Now this is salt, and this is acid. What was the concentration of the acid? 0.1. And this here is 0.2, right? Now the gave us our Ka to be equals to 1.8 times 10 to the power minus 5. Now pKa is equal to negative log Alright, so that is that for that guy. So the next thing we're going to do here would be now say pH equals to pKa plus log of the salt all over that of the acid. Now this is 4.74 plus log. Concentration of salt is 0.1. That of acid is 0.12. So please evaluate this guy for me. 4.96. So that is the pH of that buffer. But most of the times they might actually ask you to solve for pH, for the pH of the buffer when an acid is added. But let me just use this guy to explain something now. What would be the effect of adding a small amount of an acid to a buffer? It's very simple. If you add an acid to a buffer solution, remember a buffer has two components, right? The acid component and the salt. The salt component is equivalent to can be the base and the rest of them as the case may be. Plus, if you add an acid to a buffer, that acid is going to increase the concentration of the acid in the buffer system by that amount. Let's assume this guy, concentration of this acid, what we did here is 0.12 molar. And the base or salt is 0.2 molar. I now said, what is the pH of the buffer after addition of 0.1 molar HCl? Small amount of 0.1 molar HCl. Class, look up. This guy is an acid, is it not so? So this is what is going to happen here. This concentration will come to this acid and say plus 0.1. And will come to the base and say what? So as it is adding here, it is being what? Subtracted here. So the effect will not be much. Can you see what's happening here? If you add an acid to a buffer solution, that acid goes to the concentration of the acid and increase it by that amount, right? And that same amount goes to the base and do what? Decrease it by that same amount. So that whatever is added to this guy will be removed from here. So that at the end of the day, the effect will not be what? Much. Now, what if a base is added? Let's say this is an acid, 0.12 molar, and this is a base, 0.20 molar. And then they say, what is a pH after addition of 0.2 molar sodium hydroxide? Class, is sodium hydroxide acid or base? So what do you think is going to happen here? It will go to where the base is and do what? Add. And go to where the acid is and do what? That is it. So 0.005 molar. Now this is a concentration. Now, after addition, please look up. This stuff is in mole, but since a liter of water is 1 liter, this divided by 1 is still the same thing as this, right? So I will say addition of 0.001 mole per liter. After addition of this, look at what we are going to have now. Now, acetic acid plus, is this HCl an acid or a base? So therefore, the concentration of the acid will increase by this amount. Is it not so? Initially it was 0.05. It will now be plus what? 1. Please do this. This is going to be 0.051. That is the answer. Now, sodium acetate was initially 0.05. You now subtract it since it's an acid. This becomes 0.001. Please press your calculator for me. 0.049 molar. So, if you want to substitute into your Henderson-Hasselbalch equation, this is not the one you're going to use. This is before the addition, is it not so? They said after the addition, so this is the values I'm now going to use. I'll now say, did I give us Ka for this? Alright, please, Ka for acetic acid is always this. Please, Ka for this guy is this. Now, pKa is equal to negative log of Ka, which is 4.74. If you solve that guy, I already showed us how we can get this guy. So now say pH is equals to, equals to, this is sodium acetate because it is a salt, and this is acetic acid. Please don't forget that sodium acetate is a salt. I'm supposed to indicate this. This is a salt. Please can just put it down. The salt, the acid. So this guy is 4.74 plus log. Please hold up. Look up before you write. Look up, look up. Sodium acetate, concentration of sodium acetate, after you must have added this guy, was what? So this is 0.049. And that of the acid, after you must have added this, is what? Please press your calculator for me. What? So that is how we solve this guy. If they are giving us base, just do the inverse. Add it to base and subtract it from the acid.